This is a continuation of the 2018 AP Chem FRQ. We're continuing on to question 2, which is a long free response question. In this question, it starts off by providing us a balanced reaction between nitrogen monoxide and oxygen to produce 2 moles of nitrogen dioxide. They've given us a particulate drawing on the right, and they're asking us to draw the particulate level representation of the reactant mixture on the left. Here they're testing our ability to understand the law of conservation of matter. So let's take a look at what they give us. We're going to start with the data that they provide us. That is my product, nitrogen dioxide, and I have 1, 2, 3, 4. Let's just say 4 moles of nitrogen dioxide. But I also have something else left over. I have 1, 2, 3, 4 moles of my reactant nitrogen monoxide. You'll notice that I circled everything. This is probably a good idea to make sure that you are not missing anything because they're all spread out. So if we go back to the balanced reaction, I know that for every 2 moles of nitrogen monoxide, I'm going to produce 2 moles of nitrogen dioxide. So if I'm producing that many moles of nitrogen dioxide, I had at least 4 moles of nitrogen monoxide present, but I also have 4 moles left over, which means on this side, I'm going to have to draw 1, 2, 3, 4, 5, 6, 7, 8 moles of that. Let me go ahead and fill those in, because 4 of them are going to be used to produce my product, and then 4 of them are going to be left over as the excess. Okay, my limiting reactant is oxygen, and if I'm producing 4 moles of my product, I would need half that amount of oxygen. So if I'm producing 4, I'm going to be starting off with 2 moles of oxygen. So in here, I'm just going to draw 2 moles. At the end, I would double check. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 atoms of oxygen on the reactant side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 atoms of oxygen on the product side. And I've got 8 and 8. So just double check at the end to make sure that you are balanced. The next 2 parts of this question, they're giving us some thermodynamic information, and the student is referencing in the text that nitrogen monoxide and dioxide will form this equilibrium reaction to form dinitrogen trioxide. It is an equilibrium reaction. Part B, they begin with an equal molar, and it's a 1 to 1 to 1. Equal molar of your reactants. It reaches an equilibrium temperature at 298. They want you to find the equilibrium constant for the reaction. So we're going to use this information to solve that first part. Second part is they are saying if you initially start with a partial pressure of 1 atm for both reactants, will the equilibrium pressure of the product be equal to 1 atm? And you're going to have to justify your answer. So here we're going to have to go back to some information that they provide us, some of that evidence, to make our claim and justify that claim. The last part, they are saying that the student hypothesizes that increasing the temperature will increase the amount of the product in the equilibrium mixture. So we're going to have to agree or disagree and justify our answer. So these last 2 are that claims, evidence, and reasoning. So let's break this up. We'll start with BI first. In part B of the problem, we're given some thermodynamic information. We're given enthalpy, not entropy, not change in enthalpy, and Gibbs free energy. So we're given that information. They say that the student begins with equal molar of both reactants, and the mixture reaches equilibrium at 298. And they want us to calculate the equilibrium constant. Although this is not on the 2020 exam, I'm going to go ahead and solve this problem, and if you look at the formula sheet, you would be able to possibly figure out that information. Okay. First thing of notice is that equilibrium. Okay. And we would probably, if you look at the formula sheet, you would see this formula where you have delta G naught is equal to negative RT ln K. If I divide both sides by RT, negative RT, I would get ln K is equal to delta G, negative delta G over RT. And rearranging it a little bit further, you would get this. Okay. Be careful for your R value here. Your R value, you are going to want to use your 8.314, and the units are joules per mole degree Kelvin. Because we don't have any information about pressure here. They haven't given us that. So we do want to use that R value. You're not going to just automatically substitute in the 0.08. And the next thing to be aware of is they want the K value for this is in joules, but my delta G is in kilojoules. Okay, so I'm going to need to change that to joules. So if that's joules, it would be 870 joules per mole of reaction. Okay, since that is joules. So if I substitute that information in, it's going to be equal to 870 kilojoules per mole. This is all going to be negative, minus 8.314 joules per mole degree Kelvin, and the Kelvin they gave me was 298. Okay, when we solve for that, your K value should be equal to 0.70. And all my units cancel out. Remember, we're talking about equilibrium constants. It is going to be unitless. Second part of the problem, they say if the reactants are both at 1 atm, will the product partial pressure be equal to 1 atm or not? So let's go back to what we know. We see here that it's an equilibrium. We know that my K value is 0.7. So not a very large, not a very small. There is going to be both reactants and products present at equilibrium. The only way I would reach 1 atm if I start, reach 1 atm if I start with 1 atm is if it went to completion. Okay, so I would only have 1 atm of my product if I went to completion. And because this is an equilibrium reaction, there is going to be a significant amount of your reactants present at equilibrium, so you're not going to reach that equilibrium because you've got a 1-to-1-to-1 here. Part C of this problem, they say that the student hypothesizes that increasing the temperature will increase the amount of the product in the equilibrium mixture. Indicate whether you agree or disagree with this hypothesis. So let's take a look at the evidence and see what we know. We know that temperature is going to shift equilibrium because of Le Chatelier's principle. We also know that it's going to change the equilibrium constant. So what we do know, going back to the data, is I have a value for my delta H. And I notice that my delta H is negative, which means that this is an exothermic reaction. So if I were to include heat in this equation, it would be on this side. Specifically, it would be 40.4 kilojoules per mole of reaction. So if I'm looking at Le Chatelier's, my stress would be that I am increasing my temperature, okay? My relief is to remove heat. And the way I would remove heat is my equilibrium would shift to the reactant side, because it is an exothermic reaction. I am not producing heat if I go in the reverse, if the reaction proceeds in the reverse. And if the reaction proceeds towards the reactant side, that means my product will be consumed. So based upon that evidence, I would disagree with the hypothesis. You need to make your claim, give evidence, cite the evidence, and justify your answer in terms of the evidence. So in part D of this problem, we see that our product from the last dinitrogen trioxide reacts with water to form nitrous acid, and they've given us the reaction below in part I. They want us to complete the electron dot diagram of the molecule, including any lone pairs of electrons. So I'm going to go ahead and draw each atom that's present. So I've got hydrogen, it's got 1 valence electron. Oxygen has 6, it can make 2 bonds. So those ones that are already paired up, I'm going to put away from the other atoms. Nitrogen has 5 valence electrons, so it can make 3 bonds. And oxygen again has 6. Oops. I'm going to go ahead and put my other pair there. Okay, so if I were to connect all the ones that are single, that are available for bonding, I would get a double bond between those 2 atoms. At this point, it's probably a good idea to go ahead and check your formal charges to make sure that this is the best representation. And the way we check formal charges is we take the number of valence electrons and we subtract from it the non-bonded electrons, total number of non-bonded, and we subtract from that the bonded electrons divided by 2, okay? So for hydrogen, it's got 1 valence electron. So I'll do hydrogen down here. We've got hydrogen, the 1 valence electron, non-bonded, there's nothing. Our bonded electrons, there's 1, 2. You're going to count both of them, divided by 2. So that gives me a formal charge of oxygen for 0. For hydrogen, 0. Oxygen, valence electrons are 6. I've got 1, 2, 3, 4 non-bonded electrons. Bonded, I've got 1, 2, 3, 4 divided by 2. So 6 minus 4 minus 2 gives me 0. So formal charge on oxygen is 0. For nitrogen, I will do that. Down here, nitrogen, it's 5 valence electrons. Non-bonded, I've got 2. Bonded, I've got 1, 2, 3, 4, 5, 6. 6 divided by 2, which is 3. Gives me a formal charge of 0. And for this oxygen, again, I have 6 valence electrons. Non-bonded, I have 4. Bonded, I have 1, 1, 2, 3, 4 divided by 2, so that gives me a formal charge of 0. The idea is you want to get as close to a 0 formal charge as you can. So that answers DI. DII, they're asking for the hybridization of the nitrogen atom. So I'm just going to down here look at the nitrogen atom, and I'm not going to draw the rest of it. Okay. The hybridization is you're counting all of hybridization for those single bonds or for those unbonded pairs of electrons. Instead of having an s orbital or a p orbital, they're going to hybridize. If you have a double or a triple bond, that's going to be your pi bond. So we're not going to include that. And what you're going to do is look at, you're going to add together the number of atoms attached. And you're going to add to that the unbonded pairs. Not the unbonded electrons, but the unbonded pairs. And that will give you the total number of groups. If you have 2 groups, it's going to be SP, 1, 2. If you have 3 groups, it's going to be SP2. If you have 4 groups, it's going to be SP3. 1 group would just be S. Okay, so here I've got atoms. I've got 2 oxygen atoms. So I've got 2 groups that are atoms, and then I also have this 1 bonded pair. So I have a total of 3 groups. So my hybridization would be an sp2. So now we're looking experimentally at the reaction that we saw on the last slide. The student is going to produce an aqueous solution of the nitrous acid by bubbling dinitrogen trioxide into distilled water. And after assuming the reaction goes to completion, the acid is the only species produced. To determine the concentration, the student is then going to titrate that solution with a 0.1 molar potassium hydroxide solution. And the neutralization reaction is shown below. The full problem in E, you have to use the titration curve to determine the initial concentration and to also estimate the pK value of the nitrous acid. Evaluating titration curves is probably going to be on the 2020 exam, but estimating pK values may not. It is important to go over this, though, just to make sure that you know how to do it. The second part of the problem is evaluating that titration curve and determining what species is more present at a specific point. So let's break this problem down into 2 different parts. For part E, we are going to take a look at the titration curve and evaluate it. And that is to determine the initial concentration. So let's take a look at what we know. We know that potassium, here is the molarity of the potassium hydroxide. Okay, we know that my equivalence point is going to be somewhere in here, which means that 20 mLs, 20 mLs of my base is added. So I also know that at equivalence, since this is a 1-to-1, my moles of my acid are going to be equal to the moles of my base. Okay, so let's figure out how much base is present at that equivalence point. This is milliliters, so we're going to divide. We're going to actually multiply our volume in liters, so 0.02 times 0.100, and that gives me 0.002 moles of my base at the equivalence point. Since that is also the moles of my acid, and I want to figure out the concentration, I'm going to take the moles of my acid. It's going to be the same. And since I'm doing molarity, I got to divide it by the amount put in. And they told me that I use 100 milliliters of the sample. So 100 milliliters is going to be a 0.1 liters. So the concentration of my nitrous acid is going to be 0.02. Okay, so that answers that part of the question. Second part of the question, they want to estimate the value of the pKa. And I do know that my pKa is going to be equal to my pH at my midpoint. Okay, and my midpoint is going to be somewhere in this range. I know that this is at the equivalence point, this is at the start, so 10 is going to be my midpoint. And if I look there, it's going to be, this is 3, it's a little bit above 3, not quite 5, so I'm going to say that it is 3.4 would be my pKa. So the way you figure that out is you look at your midpoint, which is down in this buffer region. Part F, they're saying during the titration after a volume of 15 ml, so at this point has been added, they want to know which species is more prevalent, your acid or your conjugate base. So in the last slide, we recognized this was our midpoint. Our midpoint is, that is where my acid, concentration of my acid is going to be equal to the concentration of my conjugate base. So if I'm beyond that point, so here is, pH is a lower region, this is more present. Here now I'm starting, this is going to be greater than this. So because it's above the midpoint, my conjugate base is going to be more present. It's going to be there at a higher volume. So my NO2 is going to have the greater concentration. And we could justify our answer using this titration curve up here and what we know about our midpoint region. And that, I think, concludes our problem number 2. Look for a video for problem number 3 shortly.